So the most important work that I've done, I think, is probably the general thing is to develop ways to understand organic chemistry with computations and theory. But there are certain milestones along the way. The first of which is the use of Fukui's frontier molecular orbital theory to understand the regioselectivity of cycloadditions, Diels-Alder 1,3-dipolar cycloadditions, and of course it's been extended to all kinds of reactions. So I think that had significant impact, and still, although it's 40-year-old theory, is a conceptual way to understand things that organic chemists do all the time. At a later time, and part of these different achievements are due to developments in theory and what was possible to do at different eras. So in the 80s, when it became quite common to do ab initio calculations, we could do more quantitative things. And at that time, in several areas, but especially in the electrocyclic area, we're able to develop a better theoretical understanding of stereoselectivity, in particular what I named somewhat jocularly torcoselectivity, but also just the idea of facial selectivity in electrophilic and radical additions, something that had been understood pretty well in nucleophilic additions due to Hugh Felkin and computations later by Ahn and Eisenstein. But we really extended that into stereoselectivity in general, and I think that's had an important ongoing impact. Beyond that, when it became possible to locate transition states very efficiently, I think my group was able to develop a general understanding of the shapes and of transition states, and essentially bringing them alive in the way that ground states of molecules had been known to organic chemists for a long time because of possibilities of structural information. So now there is computed structural information about transition states, especially of cycloadditions, but we've done all kinds of things that I think also has had some general impact on the science.